screen hasn't shared yet.
It just has to be there. Cool.
Yep, you're all set.
Hello. Welcome to Ptrace Part 2. Hopefully it makes more sense than last time. We'll try. Oh God. Okay. That was a picture of Tenchi and Enzo giving the middle finger, but I blurred it out because we censor stuff a lot. So sadly it doesn't show, but this is funny enough, I guess. But okay, so if you guys remember from last week, or 2 weeks ago, I talked about Ptrace and injected into SSH, and the goal was that we were able to extract your password using Ptrace. But it didn't work for me. I was having a lot of bugs with the memory stuff. But I decided to go make it slightly much easier rather than doing something huge like SSH. We can just go with little programs like sudo. So for this time, it's less complex, and all we have to do is just observe like what exactly is executed on the system, and we just inject our command to that sudo command. So hopefully it makes sense as we go on. The same knowledge from last time when I talked about like what Ptrace is and like the different options of Ptrace still kind of applies here. So I call it the sudo injector, or dollars, whatever how you say that. It's just the name is a god of trickery, because the goal is to inject our command into your bash process and run our command instead of yours. I do want to point out I spent at least 30 minutes looking for a good name before I even start writing the code. That's when you know it's kind of good, when you spend like way too much on the useless stuff. Okay, but apart from that, the flow of this project was you first find your target bash session, so whatever the target is on. We have to set some Ptrace options, because Ptrace gives you different things to look for when you attach to a process. So we'll talk about that later. Then we look into the syscalls, because every command uses some kind of syscall. So we could just attach all of them, but that gets really complex. So we just target the one we are interested in. And this is the same memory stuff. We try to obtain the registers and whatever the data is and modify to our stuff. And we just tell the program to continue like nothing happened. So let's see how it goes. So the first thing, really pretty easy, is because in a Linux system you can have multiple bash sections, I made it slightly easier that all you have to do is just pass in the PID of that process. And in Linux, you can find that by just doing echo $$, and that will give you the process ID of whatever you're running, or that bash session. So you'll see that in the demo, I guess. So after that, you just simple attachment. You just attach to the process ID. It's going to give you a -1 if it didn't properly attach to it, or if that process ID doesn't exist. This is just me doing some error handling. The wait PID is it's important. When you attach to a process, the process might still be doing something and not exactly stop whenever you attach, so you have to wait for it. So by using this parameter, the wait PID, pass it the target PID and the status, which is what the result would be. You just do that, and if it's -1, it means that the process did not stop and it's just ignoring you, or some other issues. But it's always good to have the wait PID. It's kind of like an error handling method. So, I should have just looked at my slides. So just a little background of the process attach. The way it works, and this works with debuggers, it sends a sig stop to the target process. And like I said, it doesn't necessarily stop at that exact time. So we use that wait PID to wait for that process to fully stop before you can do anything. And as you can see, there are different like return values. Anything less than -1 is, oh wait, it's not good. The goal is if the result is -1, it's not good. So we just wait for it when it's not -1. As you can see in this quick screenshot, I'm attaching to 19859, and the status code was not 4991. That's not -1, so we're just good to like continue whatever I was planning to do. So we attach to the process. We need to set some options. Again, Ptrace gives you a lot of things to do, but we are looking for specific things. So this is just a quick list of what I think is really cool. The first one is the trace clone. This would stop the target process when it creates like a clone. So like when you do like fork a process, there is a fork, but like clone, fork, you can kind of think of them as the same, but not necessarily. So with the trace clone, it stops the process and follows the child process that gets created. So this is going to be a really important one. The next one is the trace exec. This will stop whenever that process is trying to do some syscall, and it's using the exec CVE syscall. So every time you run a command, everything gets passed to the exec CVE. I think there are different versions, like exec CVEP or something like that. But there are different ones, but most of the time they use the exec CVE. So I'm looking for that syscall. And if you really want to like prevent a process from stopping, you can also do like the trace exit and so on. But again, for my research or code, I'm using the trace clone, trace fork, and the trace exec. So after we do that, since we have those options, we just have to wait for that process to get to that moment when it uses that event. So in our case, we are going to wait for the clone, exec, and so on. So we just do that in a while loop or forever loop, as you can see. So those options are using like bit shift. So we have to also do that bit shift in when we're checking for that process. As you can see, I have the event equals status the greatest sign to 16. But if you read the Ptrace main page, it tells you like exactly like what option and the bit trace, the bit move part of it. But yeah. Wait a second. Okay, so this is what it fully looks like. We'll go back in a little bit. Oh yeah, before I do continue, I wrote this program without this last part, the Ptrace part. So if you don't have this, your program just hangs and never gives you like the command prompt. So you need to have this part, which is just saying in the switch statement, it does like a continue, which just says continue the process, like nothing is going on. So this is really important. I spent way too much time on like debugging the later stuff. So we're going to assume that something happened, and this is just using a simple switch statement. As you can see, I put the fork and the clone together because I just consider them as one. And when I see them, I use the get event message to get like the new PID because that returns the PID of the new process. And we just do that, and we do like a new process created and the number, just because it's nice to have like a log for it. So this part is just again doing some checking if there's any like signals that's been sent from the child process. To be safe, we target like the Control-C, Control-Z, and like the ones that would stop the process. So I have that in the if statement right here. And if you're really interested in what the signals in Linux are, I have like a link right there. It doesn't give you the full thing, but like gives you the most important ones that you would see. And this part, the last part, I think you guys can see it. It's just doing a quick check if the return PID is the same as the target pre-ID that we attached the first time. We're just going to tell it to continue because that's not what we're looking for. So there was a moment where we can do like a skip. So if you just want to run the command once, you can just inject and detach right away. But I kind of just skipped it over because it was not that important. But ignore that. So now we attach to the process. We find it using using the fork and the clone stuff. So we need to get the registers and possibly get the commands and whatever is being executed in that bash session. So this is where the registers are. In 202 or 201, I forgot which one it is, you talked about the different type of calling conventions. There's the fast call, there's the STD call, and I'm pretty sure there's other ones, but like those are the two main ones I know about. That is really important here because that's how you can tell like where like a specific like argument or command or syscall is placed in the registers. And like I said, we use the Ptrace get regs to get all of this information. I was stuck on this for a little bit, and I used, obviously, I looked at the Linux source and some other website, which I want to show right now. But this is from the Linux source code, where it just states that the EAX, sorry, not EAX, but the RAX. And just to note, I'm on a x64-bit VM, so it's all RA something, not EAX something. So the syscall is saved in the RAX. The return address is the RCX. The arg0, so whatever the first part is, the command would be stored in the RDI, and the rest of the variables, rest of the arguments would be in RSI, RDX, and so on. And this is me. Before I looked at, I actually like pay attention to documentations. I just did a bunch of print statement because that's the best way to debug your code. Yeah, and it works. So it correlates with what I found. Again, I'm just going to share my whole desktop because there's something I want to show. Not this one, but this one, given by Stuart over there. This is a list of the syscall table, and the cool thing about this is it tells you what, like the registers are. So in the exec CVE syscall, the first part of the function, you pass in the file name. So this is where your command is. So if you're using sudo, it's going to pass in the path of sudo. So this would be like /user/bin sudo, and that will be stored in the RDI. And everything, if your full command was sudo ls, that would also be in the RSI, and that would be an array of that whole like command, including sudo. So I think I have this linked in the slides, but this is a really good thing if you're trying to play with the syscall table. And it also points you to the source code, which makes it so easy to just read it. So we go back to the presentation. Oh, God. Yeah, same thing I just said. I'm just going to say a quick break. Is there any question about what I've said so far? Awesome. I could not explain any of this either. So like I said, with the RDI will point to the syscall, and that's what I did right here. I checked if that RAX. I said that if the RAX equals the EXE CVE, which is the syscall, then that we know there's something being executed. I wanted to play with it and do more, like using the write syscall and just edit the results of your command, but there was no time. That's more of a future project for this. But as you can see, I get the address because it's just good to have like those information. And there is a function called get_command. I'll show you what it is. And it pretty much just takes in the PID and the address of the register, and it will get the string for you. And as you can see at the bottom here, it does a if string compare, which it compares whatever that function returns to the /user bin sudo. And we know sudo is executed if that's what we get. Yes. There are moments where you write code and you try to make it as good as possible, but you just have to make it really bad. And this is one of it. And you'll see why in a moment. But so each, again, I'm on a 64-bit VM, so every word is 8 bits. So that's why I have the size of long right here. This just skips over 8 bits. I do want to say I found this interesting stuff where it's like a if-else kind of stuff. So this just says if the end of bytes is not equals to any number, then break out of it. So if you want to use a for loop and you just don't want to do like an if-else, that's one way to do it in C. Pretty cool. So ignoring that part, when we have the address, we want to get the data out of it, and we use the pick data function, or option from Ptrace, and that would give you the bytes or the value in that address. And I got stuck on this function for way too long, and I had to go to Stuart and some really Linux maniacs over there, and we were able to fix this in just 30 minutes, and I spent 2 days on this. But when I get the bytes from that data, I can just use this line right here, which just converts the long bytes into strings. And, oh, sorry, go back. And what that would give you is going to look something like this. So this is what it returns to you. So it's pretty, at first you might not know what this is, but when you put it on from a X to ASCII converter, you can see that it just reverts. You can see it is the command sudo. The reason why this is in the other like flipped is the just endian of the machine, but we can say it works right here. And I just loop over it to just put it in a string so I can return that instead. This is where that terrible part of the code is, because I literally copied and pasted that for loop and put it at the bottom and just added one line, which is this, which is just creating the string like fully. The reason why, I'm not that great at C, so also Stuart made me do it. I just wanted to point that out too. But at this point, this function will return like the command that's been executed, which you guys would see, as you can see right here. I can run the clear command, and it tells me what was executed, the whoami and ls, and so on. The x value, as you can see, is right here, the 6E6962 blah blah blah. You take that value, pop it into the X to ASCII, and that is your string. So that's something I learned while doing this project. So that's cool. But we are interested in sudo. So we can just print out the other syscalls just to like show it. But again, we need sudo, so when we see sudo, we can just break out of it and do whatever we need to do for it. And sudo detected. So the next part is to get the arguments that's passed into sudo. So what we have so far, we're able to attach the process, read the data from that memory, and detect the different syscalls that are being executed, and also detect our own syscall that we want to do. So now, like I said, next we need to get the argument that's passed into sudo. And as I noted before, the exec CVE, the second argument, will be an array of the whole command. As you can see, it's going to be like sudo ls-la. So we need to get that and override that value and execute our command instead. So luckily, we have that other function which just returns a string. So instead of rewriting that whole like function again, we can just call it instead. So what we have here is we do, again, a for loop, and we pass in the address of that whole variable. And instead of me actually trying to convert the x value to ASCII, I can just pass it into that command I created before, and that will return the value instead. And the rest of this part is just me putting all of them in a list, so it can look like an actual argument. So that's just this whole part. But like the big part is the reusability of that get command function. So that's all right here. There's a lot of debug statements. Like this shish right here is not being used, but I just left it there. But the real part is this part. Almost there, almost in the last part. This is the final part. So we get all of that information, and now we just need to edit that whole command and point to ours instead. Still using the Ptrace data, we just get more information about it. And there's a function called getRemoteString, which is similar to the get command that I created. It gets all of that data and create a list. And what we do at this bottom part is we try to allocate the same space as the original one, so we can just replace it. All of this fanciness is just doing some, again, replacement. But the big part is this part, where it's doing the memory. So we've edited the arguments, and now we just need to point the address to our command. And that can be done using all of this magic. I honestly do not want to explain this because it's still a little bit over my head. So I just know it works, and that's all I can say. But I think at this point, it's more fun to just see it than just for me to talk about it. So I'm just going to show a demo because that's much better. So here we go. Hopefully it works. Sorry for the noise. Okay, it still works. So, okay, it's good on Zoom. So this is my binary. So like I said, in order to get the PID of your target, you just have to do echo star, or sorry, not star, $, and in this case, it's 19859. So I just do this, run it, and it just attached the process. There's nothing visible that shows that it's been attached. So I'm just going to do like clear my screen. As you can see, it finds that. This is the X. We take this and you can pop, actually let's do it. Let's copy this and put it in the, oh shoot, copy the wrong one. Copy. As you can see, it's the user bin. I didn't copy the whole string, but as you can see, it's building that whole string. But we are looking for sudo. So if we do sudo, we can see the sudo is detected. This part is the get command arguments. So at this moment, I only ran sudo, so there's nothing to attach to. I should make this more readable, where it says, oh, sudo detected with no arguments. I'm just going to ignore that. But this is the before results. But if I do sudo ls, you can see it detected that I ran ls using sudo. If I do sudo id, you get this random ff, but that's just me not properly doing some memory stuff. But we have a better version. So if I go to bins right here, dulo. If I do dulo-q, which just tells it that I only want to run our command once, and that's it. So id, -q, then we pass in that process ID again. So echo 19859, and in this case we want to run ID because it's cooler. So same thing, it attached to the process. It sees that we did declare. But if I want to do sudo ls, not sudo, but yeah, sudo ls. So we expect to see sudo ls on the slash. Oh my God. We hope to see the result of ls. But what we should see when we inject into it is the ID command. So if I do this, put in my password, it shows ID instead of ls. And that's the whole program, just injecting into it. There is different options that it continuously, like nonstop, just inject ID. But that can be fun and also annoying at the same time because then they can do nothing. Actually, let's try something. I never tried to like switch to root. Let's see if that even breaks it. So if I go back, do it again. If I do sudo su. In this part, it's kind of hard to know because it didn't actually switch to root user, but it just runs our command instead. But this is pretty much the goal of this project, just to use the Ptrace and just a bunch of other debugging functionality. There is different versions. So there's Ptrace, which is process tracing. There's Ftrace. I forgot what function called tracing. There is Dtrace that I found out like a few days ago. So there's multiple ways of tracking. There's Strace, which is syscall tracing. I should look into that later. But as you can tell, there's a lot of tracking or tracing mechanisms in Linux that you can use. You don't have to use Ptrace, but for people wondering how we come up with like interesting or novel ways of doing red team, it's just you looking at what Linux has for you and using it the way you would use it as a developer and just tweak it as you go on. So that's my 1 week project before I move to another one. I never finished this. Any question about this? Oh my God, yes, Enzo.
So you said that you had an option such that it won't quit after the one command.
Yes.
If you just keep it running, and then after any command, it will always run ID.
Yep, so if I remove the options, if I do sudo su, nothing, sudo ls, nothing, sudo, if I do sudo id, you would know the difference. If I try to do sudo, what else? Sudo ip tables, nothing. So this is the fun part. It can be fun, but also annoying for blue teamers. But the way to bypass this is if you just kill your shell, get out of it, and come back inside. Because when you come back, it's a different process ID, and this process ID would be gone. So if I exit out of this, it just dies. So that's an easy way to bypass this, or as from a blue teamer's perspective. But obviously, we can tweak this where it constantly just attached to every bash process. But this is not a red team tool; it's a POC for me. So lucky you. Yeah. Any other question? Cool. If you have any question later about C, memory, I'm not good, but I can point you to people that I know can do it right there at the back. Yeah, that's all I got for you guys today. I'll see you next 2 weeks from now.